Okay, so today we're going to go over recognizing special polar graphs. By looking at the equation, we're going to be able to do that. The reason why is because sometimes when we're in, let's say, BC Calculus, we need to just do a quick sketch of our equation and then proceed from there for other applications, which we'll see on our next lesson. But we're going to graph our curves in our class to make sure that we get the correct curves and we understand fully what each shape is, because this is new to us. It's not one of our conic sections like a circle or a parabola. So if we are sketching, we need to identify the type of our polar graph. And there are 4 different types that we're going to go over. It looks like I just crossed that out. Sorry about that. And if we were sketching, we would find R at just the quadrant angles. The quadrantal angles are 0, pi over 2, pi, 3 pi over 2, and once again 2 pi. All right, so the 4 different types that you're copying down from here, okay, from this section, I kind of listed again in the next one when we start talking about the curves. So the very first type is a limacin, and it could be more specific. There are quite a few different limacins. So the first limacin that we're going to talk about is one that has an inner loop. Okay, the second one we're going to talk about is one that is heart-shaped. It's also called a cardioid. And the next one we're going to talk about is dimpled. And the last one is convex. All right. So when you get a chance, hopefully by now you copy the first part, you're up to me with the second part. So our curves can be a limacin. If it is a limacin, you will notice your equation for R has a plus or a minus sign in it. And usually there's a value before the plus or minus of a value next to either sine or cosine, does not matter, theta. So I'm listing it like that. You typically don't see it listed squished together like that, but we're just trying to save some time. So let's discuss A and B. So A is established as a constant, okay, before the plus or minus sign, and B is the constant right after it. So we're not considering the sign. So if there is a plus sign before B, then B is positive. If there's a minus sign before B, B is still positive. It's only when you consider the negative of B that you would consider sign. We don't do that. I put in red, don't do that. Let's erase it. Okay, no good. We're just establishing what A is and what B is. The number before the plus or minus sign and the number after. Once you establish what those numbers are, okay, let's say they're 1 and 2. We're going to divide them. Okay, then we're going to compare that. Either that is going to be less than 1, okay, and that gives us an inner loop, or it's not. And if it was not, it could be B, C, or D. Okay, so we can tell from the equation, if it was 1 and 2, that it was a limacin with an inner loop. So I can now go a little bit faster. So let's say the equation is, let's go to B, 2 plus 2 cosine theta. Well, here's A, here's B. There's the plus sign, so we know it's a limacin. But which one? It equals 1. So this is one that is a cardioid or heart-shaped when we graph it. So it's a limacin that is heart-shaped. So let's go to C. So let's say your equation is this one. Okay, we know it's a limacin, and we're going to take A and B, divide them. I'm squeezing it in here. 3/2 is between 1 and 2. When your fraction is between 1 and 2, it is a dimpled Lee-Mason. So that leaves us the last one here, convex. That is when your equation, I'm going to switch it up a bit, make that 3. And I haven't used the negative sign yet, so we'll do that. And I haven't used sign, so let me do that too. To just give you that variation, okay? So we can identify A to be 3 and B to be 1. Okay, it is definitely Lee-Mason. So 3/1, this is greater than or equal to 2. When it's greater than or equal to 2, then this is convex. Okay. And that's how we can identify the different types of Lee-Masons. So we're up to number 2, talking about the rose curve. Rose curve also has different types. That is because it depends on the number of petals that it has. Yes, I said petals. And yes, you may be thinking petals, rose. So it does kind of look like a flower. So the way in which you can identify it is a rose curve is that it kind of looks like a circle, which we'll talk about that in a bit. There'll be a number times sine or cosine, but then there's another number, we're going to call it n, times theta, okay? So now, we know that it's a rose curve, because it's in this format, and either it has a certain number of petals, we can identify how many petals there are depending on what n is. So if n is odd, okay, so let's say it's 3, then we say that there are 3 petals. So identify that it is odd. If let's say n was 4, okay, so once it's even, you then have to do 4 times 2. That gives you 8. There's actually 8 petals. I'm sorry I didn't fill this out. That was a 3. Okay? So there's a little bit more to do when it is an even amount that you're multiplying with theta. So let me do another 2 examples. So if r is 3 sine of 5 theta, then since n is 5, and 5 is odd, then we're going to have a rose curve, okay, with 5 petals. Now, if the equation is r equals 3 cosine, again, it doesn't matter if it's sine or cosine, of 6 theta, since n is 6 and it's even, we got to take the 6, okay, multiply by 2, and we get 12. So we have a rose curve with 12 petals. Okay, so now we know what a lot of our curves are going to look like. And oh my God, I forgot to say about a Lee-Mason, what it would look like. So we understand a rose curve and petals, what a flower would look like. A Lee-Mason, the best way I could describe it, kind of looks like a lima bean. Okay. And now we're up to number 3 with circle. Everyone knows what a circle looks like. Okay, so we're starting to get into the easier equations as far as analyzing them. Okay, so in number 2, I mentioned, it kind of looks like a circle. So with a circle, it's a number multiplied by either sine or cosine. But it's just of theta, 1 theta, n is 1. So that's why there wouldn't be any petals. With this, it just looked like one big circle, and that's what it is. So that's what identifies the circle. And it's kind of explained right there, n is 1. And for 4, so 4 is a new shape, but a lemon skate looks like infinity, either like this or like that. It could be on its side. Yes, and it looks like I'm drawing the number 8. But yeah, in order to get this kind of shape, this lemon skate curve, r is going to end up being squared. Many times there's more to the equation than that. There's a perfect square instead of just like 3 being multiplied with sine or cosine, like in the last 2 examples, roses or circles. And n is not 1, and it's not any number, it's actually 2 times theta. So this graph really likes the number 2 a lot. But the main thing is that r is being squared, so we could get like both pieces of our curve and kind of comes around. Be careful when you're using the graphing calculator, because the closer it is to a 0, you're not going to see it connect, but we know by actually doing it by hand, it will indeed connect, all right? So that's why we actually do graph them by hand, so we get the full feel of our graphs. All right then, let's go identify our equations, understand their graphs, and keep on working with our polar equations.